Welcome back to session 5 of our 6-part series called Idea to Invoice. Again, my name is Roland Robles, and I'll be the presenter today. And I have a lot of great content to show you. But before we get into today's topic, let's kind of talk about where we're coming from. To reiterate, this is a 6-part series covering a case study called Acme Audio. And what we looked at up to this point is we looked at how Acme Audio has been using the whole suite of MLC tools to solve a lot of their business needs, which includes project management, leveraging SOLIDWORKS Manage. We talked about how SOLIDWORKS PCB and SOLIDWORKS Electrical Schematic was helping Acme Audio do all their electrical design. We then transitioned over into the design automation, where they were leveraging DriveWorks to automate a lot of their mundane processes. And then last time we were together, we walked through the actual ECR, ECO, ECN process leveraging SOLIDWORKS Manage. What we'll be looking at today is we'll be looking at how Acme Audio is addressing a lot of their manufacturing needs. Now, let's start with the whiteboard and let's just talk about what Acme Audio, what their current needs are, right? What are they actually doing? Well, one of their main things is they manufacture molds for their large production quantity runs. And so these are both injection and rotary molds that they're using for their speaker housing. On top of that, they do provide custom solutions, so they end up doing a lot of low-volume custom applications for things like brackets and mounting hardware, stuff of that nature. And then the last thing that they develop in-house is they do these custom heat sinks for these specialized audio systems. So these are their 3 main manufacturing needs that we're going to be talking about today. Now, the challenge is like most companies, they are limited to their capital investment, and right now they only have one CNC machine. On top of that, they do create some low volume parts, so it is a little bit of a challenge to always justify creating a full injection mold for a low volume part. They have to develop a lot of custom fixturing to address their needs when they are doing their CNC machining. And then the last challenge for them is they really need to control the process and timing. They outsource a lot of parts right now, and one of their main goals was to try to bring a lot of their manufacturing back in-house. So, how are they doing that? Well, they've broken down their manufacturing really into 2 processes. One, they brought in additive manufacturing, or what a lot of people know as 3D printing. And then they're also leveraging your traditional CNC machining to create their injection molds. Let's first talk about 3D printing. So when we were working with Acme Audio, we really understood what they were needing to do, and we created a case for 3D printing. First thing is they couldn't afford to buy a new CNC machine to actually address all of their throughput. On top of that, they really need to be able to adjust on the fly. So they do provide a lot of high custom applications along with their OEM units. And so they needed flexibility for things that weren't just bulk manufacturing. On top of that, they really needed high strength, lightweight components. So a lot of their audio systems are going into boats or vehicles, and they needed to try and keep the weight down of their parts. And then the last thing is that they needed to be able to produce production quality parts, but at low volumes. So we're not talking about just, your run-of-the-mill desktop printer. So how did Acme Audio solve this need? Well, we worked with them, and we have a tool called Markforged, which this is the line of additive manufacturing 3D printers that we have. Markforged is an industrial 3D printing platform that is a turnkey solution. So this provided them with both the printer, the software, and industrial materials that they could actually solve all of their needs with one solution. We do this through the platform that consists of both the printers, the software, and materials. Now, one of the biggest challenges for Acme Audio is they needed to have a wide range of materials at their disposal in their 3D printing technology. Markforged part functionality starts with engineering grade materials. We have the ability to print plastics, continuous fiber composites, and metal. This means that Acme, as the user, has access to about every material that they could ever need to solve all of their engineering problems. Let's first talk about some of the basic materials that they were using in the Markforged printer. The matrix material that we use is called Onyx. Onyx was developed by Markforged, and by definition, it is a composite in it of itself. It consists of a mixture of nylon and chopped short carbon strand fiber. Interestingly enough, the chopped carbon fiber was not added for strength specifically, but more for stability and printability. The short strand carbon fiber helps prevent drastic changes as the material is heated and cooled, thus resulting in beautiful, accurate parts, which this was very big for Acme Audio. Onyx by itself is actually fairly strong, at 20% stronger than ABS and about 40% stiffer. There are many cases where Onyx by itself can provide most of the adequate characteristics for a final functional part. And this was the case for Acme Audio also. In some cases, though, Acme Audio needed a stronger part. And so in that case, they were able to leverage Markforged continuous fiber composites. Now, what is a continuous fiber composite? Well, let's talk about that technology. Composites can sometimes be an intimidating subject unless you work with them regularly. All we're doing is leveraging the strength of a composite structure to deliver a strong functional part. It turns out we can actually do this with 3D printing platform also. Composites by definition is just a combination of two or more materials combined together to achieve a desired property. For example, if you think about a composite part, this would be like when we pour concrete and reinforce it with rebar. We leverage that same technology and that same thought inside the Markforged printer. So for Acme Audio, they were able to print stronger production parts than just with a basic plastic material. The dramatic increase comes from the additional continuous fiber in the part. Markforged technology has the ability to integrate carbon fiber, Kevlar, fiberglass, and high-strength, high-temperature variation of fiberglass to your parts. Each fiber has a unique value proposition to help solve a number of different problems. For example, when leveraging carbon fiber, you can actually print parts that exceed the strength of 6061 aluminum, which this was big for Acme Audio because a lot of their parts are custom bracketry and custom components that are structural in nature of the audio system. Kevlar is a great impact resistant and energy absorption, so for high wear applications, it's a great fit. High temperature scenarios are a great fit for your high strength, high temp fiberglass. The key takeaway here is that each of these fibers were selected and engineered to allow you, the users, to tackle a wide range of problems. And this was a big reason why Acme Audio is leveraging the Markforged printers. Here you can see that by adding any one of these 5 fibers into the core material greatly increases the performance of the material and the performance of the part. Let's kind of break this down and have a better understanding. So here we have an actual custom component that Acme Audio is using in their tooling department. In this example, we are printing this part, and when we look at a cutaway of the inside of this, you'll actually see that the base material, Onyx, is represented by white lines. There is a triangular infill within the part to decrease the weight, decrease the cost, and decrease the print time, which this is huge for Acme Audio because they were able to produce parts at a much faster rate. The continuous fiber, in this example happens to be Kevlar, is printed in yellow lines, which you'll see that this is in the outer perimeter of the part. The fiber is extruded out of a second nozzle and pathed into the part as a single continuous strand, and then it's cut when finished. What this means is you're able to produce a lighter component with a stronger output. So what platform was Acme Audio actually using? Well, they're leveraging the Markforged X7 industrial platform. This is kind of our flagship printer. This is going to be what the majority of our customers, and in this case Acme Audio, is actually using. Let's take a look at a little bit about the machine specifics. The build volume is essentially roughly a little less than a cubic foot. The resolution is between 250 and 50 microns. What sets this industrial printer apart is the level of the automation incorporated into the machine. This automation exists, one, to provide a seamless and reliable experience to the user, and two, to provide exceptional accuracy. The X7 can routinely print parts within 0.02 of an inch, which this was huge for Acme Audio because they were printing production parts, not prototype parts for form, fit, and function. On top of that, there's a laser micrometer on the print head, which serves a variety of functions, including an adaptive bed level scan. So before every print, the laser is used to measure the bed flatness, which is then accounted for in the first 5 layers of the print to ensure a perfect part. The laser also helps the printer perform a pre-print calibration, which measures the actual print bed width versus the expected and then adjusts accordingly. Lastly, the laser can also be used to perform in-process inspection of a printed part. At any layer of a print, you can assign a scan, which will return a report showing the printed geometry compared to the input geometry, which is typically an STL file. The X7 is capable of printing all of the fiber materials and will print specialty materials such as Onyx FR and Onyx ESD. What this means to you and what this meant to Acme Audio is that this is printing high strength, high quality production parts. This really helped Acme Audio solve their challenge with low production volume. What that means for them is they can now keep their CNC machine running, producing the molds they need for their high volume part of the business. And they can do their low production volume leveraging the X7 technology. Now, Acme Audio really they actually have 2 kinds of printers in-house. So the first we just talked about, which is your traditional FDM plastic composite printing part. But they're actually also leveraging the Atom metal 3D printing process. The Markforged metal 3D printing process is essentially an atomic diffusion additive manufacturing. Now, why did they want to bring in metal 3D printing? Well, let's talk about their need for a second. Right here, you can see inside SolidWorks, one of their applications, which is one of the more technical things that Acme Audio is doing, is they actually design custom heat sinks. One way that they are very competitive in the market is being able to produce a high quality audio system. And the way they do this is by keeping the heat down. Now, the challenge with these custom heat sinks is they're not easy to manufacture and they can be expensive to outsource. So what Acme Audio did is they decided to think outside of the box and leverage 3D printing to solve this need. Let's walk through the Markforged 3D printing process so that way you guys can have a better understanding of what Acme Audio learned along the way. So what are we doing? We're leveraging 50 years of metal injection molding, or what some people call the MIM science process, and we're applying it to a 3D printing platform. Essentially, a raw metal powder is combined with the wax and a polymer, which is then extruded into a filament. If you're familiar with 3D printing, this is very similar to a traditional FDM style process. The process yields a raw material, which we call a filament, which essentially encapsulates the metal powder, which otherwise requires significant precautions. These spools are easy to handle and easy to store, which this was a big thing for Acme Audio. They couldn't really take on any manufacturing processes that were going to be overwhelming to their design process. Like most customers, they run a very lean operation, and they needed their manufacturing processes to be lean also. And this is why the Markforged metal printer was such a great solution for them. Now, let's talk a little bit about the printer. The spools are loaded into the printer similar to a typical FDM printer. This makes changing materials very quick and easy, contrary to a powder bed system, which require extensive cleaning during material changes and oftentimes takes multiple days to accomplish. This provided them flexibility to print different metals for different applications and their heat sink needs. You'll notice that there's actually two different spools in this image. The spool on the left is the metal material, and the spool on the right is a ceramic material that is used as an interface between supporting structures. So since this is an FDM style, we're using this ceramic support to print geometry that we might not ordinarily be able to print. We'll talk more about this here in a little bit. So what happens from here? Well, the printer process is a simple extrusion style process where it's building the part layer by layer. Markforged has iterated and optimized the printing of the suspended solid filament very accurately for the past 5 years. The robust system utilized on the X7 industrial composite printer was partially leveraged for the design of our Metal X system. Essentially what that means to you in Acme Audio is we're leveraging technology that we're already familiar with, and it's a proven technology. So how does this add-on process work? One of the big reasons that Acme Audio went with the Markforged printing was that it was simple. So they're obviously leveraging SolidWorks. So they design a part. In this case, they design their heat sink. Then they simply export that as an STL and they send it into the Markforged slicing software, which is called Eiger. That prepares the STL file and it prints it directly inside the metal printer. From there, there's a very simple wash, and then the last part in the process is the actual sintering. And this is where it's taking the powdered metal and essentially fusing it to become one solid piece. Acme Audio really liked this because they didn't really need to know anything special. Markforged is taking care of all of the intelligence into the print automatically for them. And really all they need to do, Acme Audio, is just worry about designing parts. So, how does the printer know what to do? Well, this is a turnkey solution. So Markforged and MLC, we provide a software called Eiger. This software will import your STL and then it uses algorithms to scale up your design for the printing process. And this is specific to the material that you intend to print. The nature of the post-processing steps means that the part actually shrinks about 17 to 20% depending on the geometry. Eiger will calculate this for you by evaluating the centroids of mass and geometry of the part. The software innovations developed by Markforged to accurately predict this shrinkage is the real secret sauce to the process. And again, this was huge for Acme Audio because they didn't need to know anything special. The 3D printing technology took care of all of that for them. A significant benefit for an extrusion style metal process is that the parts are printed with a closed cell hollow infill. There are a couple of reasons why we do this. One, metal parts are significantly lighter and have a higher strength to weight ratio. This may or may not be important depending on the use case. For Acme Audio, this wasn't as important. Two, a part with the hollow infill structure uses less material and thus is essentially cheaper and it's faster to print. Three, the strength properties of the part are largely conserved when this type of structure is used. In most cases, a part maintains 85% of the strength versus a solid part. Fourth, the hollow infill allows for faster infiltration during the wash phase. The solvent used in the wash must make its way through the entire part, and the migration time increases exponentially as part thickness increases. In a nutshell, it makes the post-processing that much more efficient. For work cases where the part needs to be post-machined, we do have options to increase the wall thickness to allow for machining stop. Again, we're leveraging a half century of science in the post-processing technology used in the MIM industry. We've engineered a wall station and a centering furnace from the ground to work cohesively with the Metal X printer, and it's all controlled in the same software and in the same environment. Now, one of the biggest things and a big competitive advantage for us is the printer itself. So the Metal X printer, which you'll see right here on the screen, This is what it literally looks like. You can see it has a relatively small footprint and can be placed anywhere, including even in an office. The printers run off our standard wall outlet and require very little power. So for Acme Audio, this was huge because they don't have a large facility. So they need to be able to bring in this technology and do it relatively easily. Last, let's take a look at some of the actual specifications for the Metal X. So here's some of the basic information on the Metal X system. You notice the build volume and max part size are different, and this is due to shrinkage. If you uploaded a part that was the size of the build volume, it would no longer fit into the software since it's scaled up to account for the shrinkage. The printer can print down to a 50 micron resolution for very detailed parts. In terms of accuracy, this is a near net shape process. In general, for small parts, the accuracy is plus or minus 125 microns, or plus or minus 5 thousandths of an inch. The good news is the parts printed on the Metal X can be post-processed just like a traditional part. This means that if Acme Audio printed out a heat sink that they needed to go machine later for a higher finish, they absolutely could. Also, the parts can be heat treated, welded, machined, and even tapped. So if you need a higher level of accuracy, you can always achieve that through a post-processing step. Lastly, the Metal X is capable of printing a wide range of materials. So we've seen a lot of how Acme Audio is leveraging the 3D printing technology. Let's take a look at really the second way that they're producing parts, and that is leveraging your traditional CNC machining. Now, let's talk a little bit about their CNC and their CAM needs, right? And let's whiteboard this like we've been doing everything else. Their first challenge on the CAM side was they needed to be able to stay up with the speed of the design process. This means that as the engineers and the designers are changing, we needed to be able to take those changes and produce molds and CNC programs at the same rate of speed. They really wanted to leverage a simple interface, and they were really looking for the best technology for their CNC machine. For all these reasons, Acme Audio came for us, and their best solution to do this was to leverage Mastercam for SolidWorks. In order to show you this tool better, I'm actually going to bring on one of my good friends and a special guest, and I'm going to turn it over to Brian Johnson, and he's going to go through one of the speaker housing molds using Mastercam for SolidWorks. Brian, go ahead and take it away.
So for today, I plan to show the Mastercam for SolidWorks. And during this presentation, I will demonstrate the process to create programs for a CNC milling machine to cut away material and produce a mold that can be formed to form the inside shape of one of these parts we've got here. So this is a speaker grill, and we're going to go through a demonstration to just do a very simple part and use SolidWorks to create a form for the inside of this part, and then show the process of taking that through using the Mastercam for SolidWorks to create a CNC program. So to create the program, as I said, I'll be using the Mastercam for SolidWorks, and as the name implies, it's a special version of the world's most popular CAM software, and it's designed specifically to be used with SolidWorks as an integrated feature. You know, during the presentation, I want to try to show some of the many advantages that SolidWorks can offer, not only the design engineer that's typically used this product, but also for manufacturing engineers who are responsible for creating CNC programs for the machine shop and developing the fixtures, you know, that may hold the parts during manufacturing. A lot of the questions I hear out there when we're selling and supporting Mastercam are, you know, what is the difference, you know, between SolidWorks and Mastercam? So I want to try to go through some of that. And, you know, what is the advantage, you know, using Mastercam for SolidWorks versus just Mastercam? So assume we have some SolidWorks customers out there, along with a mix of people who may not be, you know, familiar with the details of programming machine tools. So I'll try to keep this pretty generic. But the difference between SolidWorks and Mastercam is in general, is SolidWorks is a tool really targeted towards the mechanical engineering. So it has tools for design and creating drawings, assemblies for parts, where Mastercam is a tool really focused on creating CNC part programs for a machine shop. And that's really what we're going to focus on today, is creating those programs. But during the creation of programs, there's also very similar products that both of these products share, and the users to both applications can take advantage of. So to start this presentation, I'm going to go ahead and we're going to take this part and start off with something that's fairly familiar in a machine shop environment. And it's just a vise that's used to hold parts during the manufacturing process. So this points out one of the real strong parts right off of SolidWorks, and that is working with assemblies, or parts, multiple components that go together. And so SolidWorks has some assembly tools that you would not find in a typical CAM application that is more focused on simply manufacturing. One of those is the ability to quickly insert components, into your assembly and place them quickly in the location. And that's where we're going to start at here. So I've started off, I brought the part we want to manufacture. This section here represents the inside of that speaker, and we're going to create a program to cut away the material to machine that on a milling machine. So right now it just has no location in particular. I just brought it into the screen. So we want to start by placing it on that vise. SolidWorks offers some really quick tools for that lets you simply pick the faces that you want to be aligned to each other, and it will move those into place. So we start by putting it on top of the vise and against this back vise jaw. So very quickly there, I have selected and constrained that in two directions. So the part will still move back and forth, but not in the other direction. It's giving me real quick feedback on what it is looking for me to place. So for the third one, we'll pick these faces here and give us a distance apart from them, maybe 2 inches. So now we have our part placed on our vise and constrained in 3 directions. Another very powerful part of SolidWorks is the way it captures those constraints and lets us easily change them if we decide that it's not exactly what we want. When I look at it, I see I really didn't line it up perfectly in the middle. If we go back and look, we see it's recorded those features I created, including the distance between there, so I can easily change that. We may make that change that value instead of 2 inches, change it to 3 inches there. Again, this is also referred to, or you may hear the term parametric modeling, so that it's capturing those parameters you use during the design process so that you can quickly and easily change those. The last part of this process, so actually I see a couple of things. We'll come in and bring this back, go ahead and close the vise so that it looks accurate on that. And maybe move this device over here to the left. This is what we refer to as a part stop, and it's just a little tool so that when the operator loads the part into the vise, he can repeatedly put it to the same position every time. Now, having this assembly on the screen during the manufacturing may not be absolutely required if the only thing we want to do is create the motion for the milling machine. But it can be very useful in communicating the information to the users out there, or the person who is setting up the machine. You may have heard the saying, a picture's worth 1,000 words. Well, giving this picture on the screen to the person who's setting up the machine can very quickly communicate how I expect this part to be loaded and make sure everything is put in the right place. So for the next step, let's start and look at how Mastercam interfaces with SolidWorks. So far, I've really been using simply tools available in the SolidWorks product to assemble these into the position. Mastercam loads up as an add-in, and I wanted to talk about some of the differences and how it works. To start off with, for any of our customers out there who already have Mastercam, anyone who has a current license for the Mastercam product also has a license for Mastercam for SolidWorks. So if you have both products, you have SolidWorks and Mastercam, simply install the Mastercam for SolidWorks, and it will add a tab shown right here where it's added the toolpath portion of your Mastercam product to the SolidWorks interface, so completely integrated to it. So we go into the Mastercam portion of it, and we'll start setting up to actually create the program for this. The first thing we'll do is establish the orientation of how the part will sit on the machine and where what we refer to as the origin or the zero part of the part is set. And this is important information that the person setting up the machine will need to know so that he can position it correctly. So here we show some different choices for our views. It shows which way I've got the X, Y, and Z, and we have some quick tools to place that in any particular position that we may want it. But at the corner of the part, the center of the part, this is really just wherever the user needs to put it on there. All right? So once we've got that established, we've got the X, Y, and Z where we want it, we can then go into tell it the next step in the process, which would be what size material are we going to cut this part out of. So there's some good tools in here. We can simply use some tools within Mastercam that will, by selecting the parts you want to cut, it'll report back and tell you the values, the minimum values needed for the material to make that part out of, and center it up on the part for you. We'll just accept those values. We see a little feedback now on the screen where we have some red dotted lines that represent, give you a quick visual feedback that you selected your stock size, and it does look correct. With that stock size selected, we can now go into the process of creating the programs. So across the top, I see many different choices that represent different types of toolpaths, and I'll try to get into some of those individually. But for this process, we'll just assume that cutting this is something this shop does on a regular basis, and someone has already gone through and created one and saved that information, because this is a great time-saving feature. And a user would simply come in and say, I want to import from our mold shop in there. And we have some settings that are set up and predefined for roughing and finishing a part similar to this. So it loads those operations, and with it brings in all the settings, what tool we're going to use, feeds and speeds that go with it, how it's loaded into the particular holder we want to use today, and all the details that control, or all the parameters that control the cutting motion in here. The only thing that's missing on this, and is going to change with every job we do, is the model geometry. So we'll go to the model geometry, and for this example, we'll say, I want to cut this part. All right. We'll leave everything else set the same on that. Now we'll let the system rebuild those cuts. It'll take a couple of minutes. While it's doing this, this is a multi-threaded application. It actually didn't take very long, but on processes that do take some time processing, it does let you continue work with the software, and it will process that in the background. So what we've created here at this point is you see some blue lines on the screen, hopefully. This would be the rough and finish operations in here. So if we go through those individually, we kind of see this second one is just motion around the part, and it uses a little different tool. It uses something we call a ball nose or spherical shaped cutter for that. We have some tools where the user can quickly verify that it's doing what he wants. Go through here and see the tool move around it. Quickly place that tool at any part along the any point along the part and look at it, make sure it's again doing what we expected. So this motion here is just going around the part, finishing the tapered sides of this part, the part that the roughing tool could not get to. So this is an important part of the interface, the ability to quickly look at a part, create your tool path, see what it's doing, and it's called referred to as simulation or verification of the process. And we have several tools for that. Another more detailed part of it is we may look at it and have it show the raw material shape. So we're going to switch to another screen here. Hopefully this comes up, and can show it starting with the material, or even go ahead and load that onto a machine and simulate what it's going to look like out in the shop on the particular machine that we're going to run this on, and simulate the process there. So now we see the tool moving, and we see it removing the material too. And there's several very important aspects to this. Other than just verifying visually that it's doing what you want, we're also checking to see, do any components of the process, such as the holder or the cutting tool, is there any interference out there? Are there any collisions? You know, is the machine large enough to do this? Slow that down a little bit. You can see that moving around the part. There's a lot of components moving. I hope that's simulating okay in the web presentation there. So during this process, it's giving me some information you see across the right. It's also checking to see, is there any collisions during the process, and you know, can this part fit within the constraints of the machine itself. There. So back in the SolidWorks interface, we've created a program. We've went through verification, simulation. We're happy with the results. The last step in this process would be to create the actual CNC program for it. So with that, we'll create what we refer to as running the post processor, and that is the point where it actually creates the program, or the deliverable in this case, that we're going to take out to the shop floor. So this represents the instructions to cut the program in there. All right. So we've created that. We've gone through the steps of bringing a part in, creating the CNC program. Before we finish up, though, I'd like to also show another huge advantage to using Mastercam within the SolidWorks environment, and that is the ability to adapt to changes that are made, because we are actually working on the same part in the same environment that the designer is working on. So if they are at the same time, or come in here and make any changes to the part, in this example here, we're going to make a change that changes one of these to a more radiused side on the inside of the part. Because we have used this part to design our mold, and we are cutting that in our assembly, any changes to this should reflect all the way down to the part program we're creating, so that you don't have to reopen the file. So immediately when we open that file, it lets us know that one of the changes has affected our Mastercam toolpath. We see those changes already in the part, and all we have to do is just rebuild our toolpath for that new shape in there. So this lets us start our process of the fixturing the part, putting the toolpath operations to it, even before the designer is completely finished with it, knowing that any changes he makes are going to automatically be reflected in the part we're cutting here. Trying to think other advantages to really using it as an integrated product. You know, really one of the biggest ones I see is for people who already know SolidWorks. So if you're already a SolidWorks user and you are working in the SolidWorks environment and are familiar with that, and you're now ready to start creating CNC programs, well, there really is no need to leave the environment you're familiar with. You know, just simply start the Mastercam add-in and use those tools. You're still in SolidWorks. You still have all access to all the tools that SolidWorks has. There's really no reason to leave that environment there. I guess the only big downside to it is for those users who do not use SolidWorks, it is important that you learn SolidWorks. If you're going to use Mastercam for SolidWorks, you really need to know the SolidWorks product because, again, you are inside SolidWorks when you're using this.
Thanks again, Brian, for showing us how Mastercam for SolidWorks can really accelerate the speed of the CAM process. Now, before we turn it over for our Q&A session, let's talk about where we're headed into our last session here in a couple weeks. So today, again, we looked at how Acme Audio is leveraging 3D printing and Mastercam for SolidWorks to handle a lot of their manufacturing needs. What we're going to look at next time is we're going to look at how Acme Audio is leveraging a tool called DelmiaWorks, formerly known as IQMS, to handle all of their ERP or Enterprise Resource Planning needs.